Thank you for the kind introduction. A very good morning to all of you. It's still an early morning, so I will try to reward you for your early presence. So twin pipe pumping method, I will explain in a minute what exactly it is. It has been worked on by Tao Yashin, who did his PhD in Ghent and is now a postdoc in ETH Zurich. And I also want to acknowledge my colleague Kim van Tittelboom, but I will do the presentation this morning. So, 3D concrete printing, of course, you're all familiar with 3D concrete printing. You know that we want to get away from mold cast concrete, where the formwork takes a large part of the cost, while in 3D printing we don't have formwork, we don't need formwork. Mold cast concrete is labor consuming, might take a long time before it can be demolded, etc. In 3D printing, we want to go to automated construction in a more rapid way with shorter durations. Of course, this is a nice desire and it's easy said, but it's not so easy done because there are some contradictory requirements for your material. Because first, typically, you have to pump your material to the nozzle, and then the material needs to be flowable enough, pumpable. And then once in the nozzle, you want to actually build the layers. At that stage, the material needs to be buildable. So you have to go from a transition, let's say, from something that is more flowable, pumpable, to something that is more stiff and fast settling. There are systems on the market, 1K and 2K systems, so 1K, one component systems. They work, but typically, let's say that the building rate is somewhat limited because at some point you have crushing of the bottom layers, quite often also some buckling failures. So the 1K systems are limited for these reasons. 2K systems, two component systems are faster. You can have higher building rates, but up to now the classical systems for two component systems are more complicated. You have some dynamic mixers inside the nozzle, which are mechanical systems requiring energy, exposed to wear and things like that. So it's not so easy. So starting from these two situations, we started working in Ghent on a new system, what we call the twin pipe pumping. Twin pipe, as the name is suggesting, we have two pipes. So we have two streams of material that are pumped towards the nozzle, and then in the nozzle they are mixed, but not with a dynamic mixer. In order to make it as simple as possible, it's with a static mixer. And the trick is of having, let's say, a final mixture and knowing how to split it up in two separate streams that you can easily pump with a large open time, so that pumping is never an issue. And then the other trick is, of course, bringing these two streams together in the static mixers and making sure that what is coming out of it is a fairly homogeneous material. So basically, this is the base technology behind the system. And so the full mixture that we want to obtain at the end, so the combined mixture with a fast stiffening property, we split it up in two separate streams. In the first application, we had a first stream consisting of sand, Portland cement, water, and superplasticizer. As such, it's having a long open time. And a second system is a limestone filler-based carrier, also with sand and water, superplasticizer, and an accelerator. As such, the second stream is also having a very long open time, but once they come together, the accelerator then comes in contact with the Portland cement and the thing is accelerated in a very fast way. So that is the principle. And this has been firstly demonstrated already several years ago, and it was so successful that even after only a very limited number of trials, we could print a 3-meter high column within 9 minutes, which was very fast. And I think it still is very fast. So this was a record speed, let's say, in printing. We went into further details on the development, optimizing the system. An important question is, of course, how many mixing elements do you need in your static mixer? Huh? So we did studies with different number of mixing elements, 12 to 30. In our system, the elements, the mixer elements had an inner diameter of 32 millimeters, sorry, and the length of each element is about 45 millimeters. So then the first thing you have to check is what about the homogeneity of the mixed material at the end of the static mixer. And there we went into some coefficient of variation. I will not go into the detail of the definition, but the lower this coefficient is, the more homogeneous your material is. Huh? So you see that, of course, the number of elements, of mixing elements you're considering is having an effect on this homogeneity. Huh? So for a higher number of mixing elements, you see a lower coefficient of variation pointing to a more homogeneous material. The price we pay is a somewhat higher pumping pressure, of course, because you have more obstruction. There are more mixing baffles, mixing elements in your way of the streams. Huh? So you here see the blue and the red line, the pumping pressure in the two separate streams, the A stream, the B stream. Then we further went into detail about this mixing process. We did some modeling, not very detailed. And from this model, you can then cut slices and check for different types of static mixers. You have on the left side of the slide the different, let's say, architectures of the mixers, KSM, LSM, etc. So those are different types of static mixers that are available. And then you see cross sections after the first one, after the second unit, after the third unit, etc., etc. Of course, in the beginning, you see separated colors, red and blue, the two streams. But the further you go, the more homogeneous the material becomes. And at the end, it's really a quite homogeneous distribution of the blue and the red particles in this model, so of the two streams and coming to a homogeneous material. So this was modeling, but we also verified this in an experimental way with CT scanning. And for that, we made mixing elements in plastic that we could get rid of later on. Of course, we had to support them in a steel tube in order to withstand the pressure inside the mixer. So we filled the mixer by having the two streams coming into the mixer, and then we stopped and let the material harden in the mixer elements. Then we sent the whole thing, so here you see the whole process. So we printed the mixer elements, put it into a steel pipe to make our twin pipe pumping system, then material filling, let it harden, and then have it sent to the CT scanner. And here you see some video of the CT scan going from the beginning of the mixer to the end. So in the beginning you saw a division of zones without white elements. Those are magnetite aggregates. In one of the two streams we have put in magnetite aggregates to have a distinction in the CT scans, and in the other mixture it was normal aggregates. So and at the end you see that the white particles are well distributed all over. You see the black lines are the elements of the mixer. Oh, here we are at the end. Here it's starting again, so in the beginning. Also here you can make these slides as we did in the numerical model, but here it's now experimental result, and it's really confirming very well our experimental observations. So at the end of something like 12 mixing elements, we have very good homogeneity of the material. So this was, let's say, modeling background and an experimental background to optimize our number of mixing elements, etc. Then another challenge is, can we upscale it to coarser aggregate? Because that would be a nice thing to do, having really concrete printing instead of mortar printing. So here we had, let's say, an upscale in diameter of the tubes and of the mixing elements, etc. So we went to aggregates size 8 millimeter. For the rest, the same principle, two separate streams, bringing them together in the static mixer, and then extruding the layers. Here you see the left side, the two streams, each of them having coarse aggregates, and the final results is a nice distribution of all the coarse aggregates. We took different types of coarse aggregates in the two streams to distinguish them very well. As a comparison, you see on the right hand the mortar, and in the middle pictures you see what the effect is on one mortar and one with a coarse aggregate. Okay, so the system was working very well, based on our let's say, combination of stream A, Portland cement-based system, and stream B, a limestone-based system with an accelerator. But we had other variations in possible mixtures. The only thing is, the final mixture you want to have, you need to find some way to split up into pumpable and long open time mixtures. So on the top you see some other Portland cement-based systems as a stream A, but with some other varieties of B streams. For instance, limestone-based with redispersible polymer, and or borated calcium sulfoaluminate cement. We also can go to alkali-activated systems, and that's the bottom part of the slide. So for instance, the A stream is a calcium sulfoaluminate cement, borated to retard it. And then we have in the B stream a limestone filler-based carrier, but with an alkali activator inside the system. And once the two come together, you have a very flash setting of your green alkali-activated material. And it is very fast. That's what you see here. Here you see the penetration resistance, which is some kind of measure of strength development, let's say, stiffness of the material. You see some curves, twin pipe 1, twin pipe 2, which are measured penetration resistance developments as a function of time with our TPP system. Commercial product with a normal accelerated dosage of 3% is given in the blue line on the right side, which is much slower. And as a comparison, we accelerated the commercial product, and we had to go to around 10% of accelerator to come more or less at the same level as the twin pipe pumping options. We can also fully automate the process. So there is some code behind. I will not go into detail, but we can program the whole system to at some point stop printing, and then at a later stage start printing again, etc. So it's fully automated. I will show some videos. The whole technology allows you to print challenging shapes. Twisted, spheroids, very large overhang. All of this is possible. And as a large-scale demonstration, we had two specific cases that I want to show you now. We had a fast column printing, also, well, it's not 3 meter in this case, 2.7 meter, with some twisted shape, complex shape. And we have volt printing, so it's like printing a window, like in the medieval cathedrals. We printed that. By the way, there are many more videos and photographs on our YouTube channel. You can do that, but I will quickly show a small compilation of the two cases. So here you see the column printing. The printer is starting with the complex shape. Actually, it was a little bit inspired on the Sagrada Familia in Barcelona. And then the printing is going on. You see some mounted video here. And then within a couple of minutes, 9 to 10 minutes maximum, the whole thing was printed. And then the second case, we had this volt printing, so the robot printer, where the nozzle is fed by the two pumping lines, the two separate streams. You see the mixer, the static mixer mounted with the nozzle, and then they are printing first the right element and the left, and then at some point it continues filling the gap. As a last example, I show you also a topology optimized bridge that we have printed. There was one group of students working on topology optimization, and I think we might have some further details in the second presentation on this topology optimization, so I will not explain in detail. So it's basically saying where is the material the most useful and where should we print it and where not. And this topology optimized bridge was then printed with a twin pipe pumping system. The two halves were printed in a vertical position. It's not going as fast as in this video. It was a little bit slower, but the video is accelerated. And then the two printed pieces are mounted together, pre-stressed, and there is the final bridge, topology optimized bridge. Our twin pipe pumping technology is patented technology. You can find this in the patent literature. And I think I have to come to my conclusions now. As a summary, I can say that we developed new 3D printing, concrete printing methodology, which we call the twin pipe pumping. It's based on two separate streams and chemical activation within a static mixer. It combines easy pumping with extremely fast stiffening rate. It enables high construction rate with good shape stability. 3 meters high column in 9 minutes is our record time. And it can be extended to larger aggregate size, for instance, and also to more sustainable alkali-activated materials. We welcome your feedback or your questions, and thank you for your attention.